Hi, this is Liam McQueenie, presenting my project number 48, Access Floor Systems for Office Use. So this first bit is just the overall context for the project. So the goal with this project was to design the reinforced concrete floor system for a multi-story office building that includes slabs, beams, columns, and footings that can safely carry the office loads given the project description. For tools, I used AutoCAD to draw the framing and the details, and then Structure Point programs, SP Slab, SP Beam, SP Column, and SP Mats for the analysis and design, and then also the Excel summary sheets for pulling together all the important numbers. And here are the main design parameters I worked with. The building being laid out with 20 by 25 foot bays, 4 in the one direction, 3 in the other, considering 3 floors. I also followed ASCE 7 for the access floor office use, giving me 50 PSF live load and 20 PSF superimposed dead load. And material-wise, I used 4 KSI concrete for slabs and beams, 5 for columns, and 4 KSI for the footings with grade 60 rebar. So structurally, we've got cast in place slabs spanning between beams. Those beams run along all the grid lines in both directions and frame into columns at the intersections. Down at the foundation level, the columns and walls bearing on the spread and wall footings. So the load path being slabs to beams to columns to footings to soil. And to actually design everything, I first used Structure Point, all of those sub-softwares, and then AutoCAD afterward. And here's my grouping approach. Pretty self-explanatory here. Now I'll go into the 4 design examples. Firstly, I chose slab SR, representing the roof slab. So this is a 6-inch slab spanning 20 feet with a 25-foot strip width, designed for a factored roof load of about 136 PSF. So using slab, I got the negative moments over the supports and the positive moments of the midspan for that strip. For those, I calculated the required top and bottom reinforcement, in the end being number 4 bars, which provided greater than the required steel for both critical and negative positive, critical negative and positive moments, which satisfying the DCR under 1.0 as well. Next, I'm choosing FBIX, the interior beam running in the X direction. This beam spanning 20 feet between the columns and carrying a tributary load from the slab. Modeled as a continuous beam, so you see the negative moments at the supports and positive moments in the span. I use those peak moments to size the top steel over those supports and the bottom steel at the midspan, providing reinforcement of 3 -7s at the top and 4 -8s at the bottom, which met or exceeded the required areas. Next up, column C3, the interior column group. Each C3 column is 12 by 12 with a 5 KSI concrete and 4 number 8 bars at longitudinal reinforcement. From the load combinations, the governing factored axial load would be about 90 kips with a relatively small bending. When I plot that point on the SP column interaction diagram, it lands well inside the capacity curve with a DCR of about 0.22. So lastly is the design result for footing F3, which supports that interior column C3. F3 is a 8 foot by 8 foot spread footing, 24 inches thick. The combination of dead and live load from the column was used to size it so that the soil pressure always stays below the allowable bearing pressure. And using SP mats, I checked the bending in both directions and designed the reinforcement being bottom number 5 bars at 8 inches and the top number 4 bars at 12 inches, providing more steel than required in each direction. And here we have the 3 figures for contour maps, 1 being pressure down, 2 being the ASX bottom, and 3 ASX top. And lastly, I just want to wrap up with the discussion in summary. So discussion first. In terms of assumptions, I mainly used tributary areas to distribute the loads to the beams and columns, treating the soil as having a uniform allowable bearing capacity under all the footings. For the controlling load cases, the columns are mostly axial loaded, with bending playing a smaller role for my example column. One of the bigger challenges was keeping everything consistent between all the different softwares. Um, to deal with that, I spent time cross-checking dimensions and used the Excel summaries to quickly see whether provided steel was always greater than or equal to the required steel, and whether all my DCRs were under 1.0. So just to summarize everything, I designed a reinforced concrete system for this office building using slab SR, beam FBIX, column C3, and footing F3 as the representative members for each of those groups. Use AutoCAD for the framing layouts and detailing, structure point plus Excel to run in the ACI design checks and organize those results. The final design satisfying the strength and serviceability requirements for load, soil pressure, and reinforcement. Overall, this project helped me get more comfortable with load paths, tributary areas, reading moment shear and interaction diagrams, and also just dealing with presenting these results in a way someone can actually follow. So thanks for listening.